So this is a video on Chapter 2, Section 4, which is about different types of graphs other than just a histogram. So histogram is a really useful and popular type of statistical display, but this case we're going to go over a few other kind of popular ones here just so we have some variety in our toolkit. So a frequency polygon is basically kind of like a barless histogram. Instead of using bars, it just uses points. It's kind of like a line graph almost, but it's good at showing trends or comparison between two data. So again, it basically does everything a histogram does, but it shows in terms of a line graph sort of thing, more of a trend type curve to it rather than just sort of categorical data almost. So let me show you an example of one here, and that's kind of blurry, so let me zoom back out to my original ones here, and then I showed a little bit better there. So these are two examples of polygons. I believe these are showing the ages of best actresses, or in the second case, the ages of best actresses and actors. And you can see again how frequent each common age is here. So it looks like this 44.5 category, which again, they're using the midpoint formula version. So this is probably a midpoint of a class here. But there's about, looks to be about 13 or so people in the 45.5-year-old range that won best actresses in this case here in the data that they're using. But again, it's really similar to a bar histogram. So if you made these into bars, it'd be roughly the same sort of shape or outline. But because it's a line graph, it's kind of easier to tell trends. So you can kind of see that the ages for best in the second case especially, the ages for best actresses were a lot younger than the ages for best actors. By comparison, which would be kind of a hard thing to see in a histogram version. So having a polygon or a frequency polygon here allows you to compare data a little bit easier. Let's go to another one that's going to be very similar to this. So an ogive, excuse me, an ogive is basically like a line graph, but it's used really for cumulative data. So an ogive should never drop in value because it's that rolling sum thing we talked about last time. So it's usually good to show, again, how stuff has changed over time or how quickly something has climbed over time. For example, let's say you're tracking, I don't know, the amount of population that's been affected with a certain virus. An ogive can kind of show you, if you're tracking the accumulation, show you what time frames the viruses was really infective and people were getting a lot sicker or a lot more infective a lot quicker. And then you can kind of see the part where the virus starts to level out and maybe not infect as quickly or as much, depending on how the ogive curves and stuff. Sorry, I got a tickle in my throat. Again, ogive is usually used exclusively, or not usually, but is used for cumulative frequencies, not normal frequencies. Dot plots is another one. So dot plot is something you probably are all familiar with. You just have a number line, you put a dot above a number each time you see it in the data set. So again, here are the ages for best actresses put in a dot plot. It's very similar to a histogram, except that instead of bars, you have dots. And instead of just categories, you have an actual number line that you use. And again, notice how they didn't label every single number. They just kind of did every second or every eighth number or so to make sure that it wasn't too cluttered. But again, it's usually good about seeing where there are groups of data. So here you can see that there's a large grouping of data points around here between the 24 and the 43-ish range there. 24 and 43 are usually the common occurrences there, and then you have a few smatterings of dots outside of that section. So dot plot's really good at showing you sort of accurate chunks of data rather than just kind of the overall estimation that a bar or histogram would. So pie charts and circle graphs, depending on what you call them, are another kind of common data display. They're usually used in terms of percentages, and they're usually based off of, as it says there, a circle. So one thing you should know how to do is sort of get and decipher how much of a circle graph should be allocated to each data set. So for instance, let's say you're tracking the favorite color of people and you asked them whether it was red, blue, or green, and these are the responses you got. And you want to make this into a pie chart. And they ask you, okay, how big should the red slice be? How much of the pie should the red slice take up? So the way you figure that out is you first figure out what's your total frequency. So 20 plus 35 plus 8. So if I do 20 plus 35 plus 8, I get that my total frequency is going to be 63. So 63 total. So how much of that 63 is red? Well, red is 20. So red is 20 out of that 63. let's convert that to a decimal here. 20 out of 63 is 0.32 essentially, which is about 32%. So the red slice should take up about 32% of the graph. So once again, that asks us, well, how much of the graph is that? Well, if it's a circle, that means the entire graph is 360, and I want 32, so 0.32% of it. So I take 360 times 0.32, whoops, and I get 115.2 degrees. So the red slice should be about 115.2 degrees in order to accurately represent, I don't know why that line popped up there, in order to accurately represent the data set. So that's how you get how much of the graph should be allocated to each category there, is you simply take the category, figure out what percent of the data set goes to that category, and then that would be how many degrees out of 360 you should give it in the pie chart. So I do the same thing for blue, except I would do 35 out of 63, and then multiply that to 360. So let's say you have this data set here, this pie chart here, and it asks you for the number of seniors. So not the percent, but the number of seniors that make up this school. We see here that seniors are the blue section. So that is the 26.9. So if there's 26.9% of this pie chart here is seniors, that means I'm going to take 0.269 times, it says here that we have 223 total students. So 0.269 times 223. This is basically doing the backwards version of what we just did. So I get 0.269 out of, or times, not out of, 223. Gets me about 59.9, or if I round that like I should, about 60. So that's 60 of the students out of 223 students are seniors. How do I know? Well, again, I just took my percent, I changed it to a decimal, and then I multiplied it by the total number of students that was surveyed or asked. And I do the same thing for the sophomore. So what degree of the pie chart is the sophomore slice? So the sophomore is the red section. This is the sophomore. What degree of the pie chart should that slice be, or is that slice? Well, again, we do the kind of same thing. It's 17.9% of the entire population is sophomores. So 0.179 times, now I'm not going to do 223 because it doesn't say the number of sophomores, it says the degree of the slice. So 179 times 360 would be what I do. That's just annoying as heck, isn't it? Let's try that again. So 179 times 360. Okay. Again, the reason I'm times it by 360 in this case and not 223 is because this wants the degree of the slice, unlike here where it said the number of seniors. So again, read your questions very carefully so you know whether to times it by 360 or by the total amount of data points you have. So this would be roughly 63.4 degrees if we round. 63.4 degrees would be the degree of that red slice there, and it looks to be roughly about 60 or so degrees. So that seems to be a pretty accurate slice there. So again, if it asks you for the number of something, you take the percent, times it by the total number of people in your survey. If it asks you for the degree of something in a pie chart, you take the percent and times it by 360, because again, there's a total of 360 degrees, and in this case, my sophomores should make up 17.9% of that 360. Come on. So stem and leaf plot we did in the previous lesson, so I'm not going to spend too much time on it here. But again, you know you have your stems on the left side, usually your tens column or so, and then your ones place or your decimal points if you're doing a decimal version on the right side. And again, it's just an easy way to sort data and sort of see trends and all that. So it's kind of like a histogram, but just a little bit different take on it. Pareto chart is a little bit of a new thing. So a Pareto chart is nothing more than a histogram in order or a bar graph in order. So a Pareto chart is more qualitative, not quantitative. So it does categories. Like down here, we have parking difficulty, sales rep, poor lighting, different types of complaints people filed. This is qualitative, not quantitative, because these categories deal with quality of stuff, not number of stuff. But the key thing about the Pareto chart, the very, very key thing, is that it always goes in order, with the tallest or the most amount being on the left side, and then it decreases as it goes to the right. So it starts with the highest category, and then the next highest, and then the next highest, and the next highest as it goes down and down and down. So a Pareto chart is always in that order. Tallest category or most category first, second, third, fourth, fifth, as it goes down the list there. If it's not in order like that, then it's not a Pareto chart. This line here doesn't necessarily need to be there. This line is just kind of an extra bit on this particular graph. I just couldn't find a better image. So you can ignore this line there. The main thing is these bars here. And again, notice how they go in order from most amount of complaint category, which is parking difficulty, all the way down to the lowest complaint category, which is clothing shrink. So how do we know whether to use a Pareto or a pie chart? Because they both kind of do the same thing, really. Most companies use Pareto charts, though, because it allows you to kind of see the disparity of the different categories a little bit easier than a pie chart would. So usually, if you want to show kind of the percents of stuff, that's where a pie chart really shines, is when you deal with percentage data. But if you just want to show kind of the disparity of, this one category is making up such a big chunk, that's usually when companies use a Pareto chart. A Pareto chart, because again, it's easier to see the difference and you can get a little bit more of an accurate estimate of the difference, and it's just usually easier to decipher and look at because a Pareto chart is already in order, whereas a pie chart might not be quote unquote in order, depending on how you look at it. So Pareto charts is usually easier to show that this category is overtaking these others by a lot. Oops. Scatter plots are, again, something you learned probably way back in math class. That's when you just have a bunch of data on a graph that kind of makes an arrangement of dots there. And scatter plots, although we do a lot with them in second semester, just to randomize them here, they're usually good at showing trends or especially correlation. They're usually good at showing whether two things have a common theme to them or an inverse theme to them or no connection at all. That's usually what scatter plots are used for, to see if stuff is correlated or not. So that's a really big use for them, is to show whether something's correlated or not. So there's three types of correlation a scatter plot can show. You can have a positive correlation, which would be something like this, where the scatter plot kind of goes up in a sort of linear fashion. Not always, but the general trend is upward. So a positive correlation has an upward trend, and that usually means that if you have X and Y category, again, that line there is going to be so annoying. Only does it in this type of lesson too. I'm not sure why. But a correlation means that a positive correlation means that as X goes up, Y goes up. So let's say your X was tracking, I don't know, the temperature, and Y was tracking ice cream sales. So as temperature goes up, the ice cream sales usually go up because people want to buy it to cool off. Or you could say age and height. So as your age goes up, your height goes up. Those are usually going to be positively correlated. Again, for most people, some people might level out at a certain age. For those of you that are the shorties among us, or some of us might actually shrink a little bit in our older age. But in general, age and height have a positive correlation. As one goes up, the other goes up. You can probably guess what negative is now. A negative is when you have a downward sloping line, so stuff like this, or a downward trend. So you're going down, and that usually means that as one variable goes up, the other variable goes down, or vice versa. So again, the x could go down and the y could go up. So something like this, another example of an inverse might be, let's see here. Inverses are usually hard to think of off the top of my head because not a lot of things are inversely related that come to mind quickly. If you talk about, say, the amount of vacation days you take and the amount of pay you get from your work. So the more vacation days you take, the less you get paid because you're not working as much. So that would be an inverse relation. As you take more days off, you get less pay in your paycheck. Again, obviously that doesn't work with everybody because some people have paid days off and all that, but in general, the overall trend is that if you work less, if you take more days off, then you earn less money because you're not working as much. So that would be an example of an inverse relationship. As one goes up, the other goes down. Or it might be that, the more time you spend studying, the less time you spend sleeping. Those would be an inverse relationship. You study more, you sleep less, or you sleep more and you study less. That's an inverse relation. And then neutral are things that have nothing to do with each other. So neutral usually is just one big scattering of dots there with no real trend. There's kind of one big amorphous blob. And that usually means that x and y have no relation. So an example of a neutral correlation might be something like shoe size and amount of money spent on hair gel. So as your shoe size goes up, the amount of money you spend on hair gel probably doesn't have any sort of correlation to it. You probably are going to spend the amount of money on hair gel that you usually spend no matter what. People with bigger shoe size do not necessarily spend more money on hair gel, at least not by intuition there. Or you can say a person's age and the amount of money they spend on cars. So as you go older, you don't necessarily spend more money on cars. If anything, you might even spend less money on cars. But that would be an example of a neutral correlation. Your age does not impact the amount of money you spend on cars. The amount of money you have to spend usually probably impacts the amount of money you spend on cars, not necessarily your age. There's probably a lot of young people who have made a lot of money that can spend that on cars, and there's probably a lot of old people who don't have a lot of money that can't spend that on cars, and vice versa. There's some old people that are really wealthy that can buy a lot of new cars, and there's some young people that don't do so well that can't buy a lot of new cars. So there's really no correlation between your age and the amount of money you can spend on cars, because the two and two don't have anything to do with each other. So those are the three types of correlation you can see from a scatter plot. Either the two things agree with each other, the two things disagree with each other, or the two things have no correlation at all. So that's it for this lesson here. Just want to make sure I was at the end there. Again, if you have any questions, let me know. The main takeaways here are just to know kind of how to identify each type of statistical display. So how to identify an ogive, a scatter plot, a histogram, and knowing kind of what scenario to use each. So you use a Pareto chart to show the disparity of different categories. You're going to use a pie chart to show percentage taken up of each category. You can use an ogive to show trends over time for the cumulative data. You can use a scatter plot to show correlation, that sort of thing. So the key items that you would use each type of graph for, that's the main takeaway from this lesson. So if you want to go back and look at those again to refresh yourself, you can. Always ask me questions if you want. Otherwise, hopefully this helped you out. Have a good day.